To understand Stokes' theorem, I want to revisit Green's theorem in 2 dimensions, but I'm going to view it as sitting inside R3. So we have a region D, the blue region inside a plane, bounded by a simple closed curve C, and a vector field that happens to be again lying in the 2 dimensions. We can view all of these as being 3-dimensional objects that happen to be flat. Like F is a vector field but happens to be only dependent on xy coordinates. Now the familiar form of Green's theorem says that integrating F along the boundary curve is the same as integrating this mixed partial derivatives of them inside the region D. So a 1-dimensional integral, a curve integral, is equal to an area integral of a different thing that is given in terms of derivatives of f. In fact, it's actually just curl of f, but since curl of f by definition is a vector, and if we view f as a vector in 3 dimensions, then curl technically is qx minus py times the vector k. So it's a vector which has 0 j component, 0 I component, and k component is qx minus py. So for the equality here to hold, I have to dot product with k to get rid of the vector part of that. And yet another way of seeing this is that I can say that this is equal to integral along D of the surface integral, so curl of f dot ds. So this in terms of definition of integrals over surfaces, over parameterized surfaces, for instance, in 3 dimension. So I will be interested in this equality that has been obtained between this line integral and this surface integral of the curl. Integrating a vector field along the boundary of a surface is equal to integrating its curl over the surface itself. And that is the claim of Stokes' theorem, that this holds in much more general surfaces, not just the flat ones here. So Green's theorem is a very special case of Stokes' theorem. For the statement of Stokes' theorem, we have 2 questions about orientation that has to be settled. One of them is, in what direction do we orient the boundary C? And then what normal do we pick for the surface? So by assumption our surfaces are orientable, we can choose a continuous collection of normal vectors at every point, but also minus of those vectors will work as well. So which one is the right one? The answer to that is that the vectors in this order, r prime of t, the tangent to the curve, so the vector r prime of t, and then the inward vector which is a rotation of r prime of t. So if we move in the closest direction and we move into the region, so that will be the inward looking vector. So this is not the picture may be misleading. So this does move into the surface. It lies in the surface. It's tangent to the surface, but instead of being tangent to the curve, it's perpendicular to it. And then the normal of the vector that we choose, so this normal vector that we have, well, in this picture maybe this will be more realistic if I can get it to be through here. So this one, and this is sticking out of the surface, will be, so the right orientation for the Stokes theorem will be that these three are compatible. So these are positively oriented. And for that, if we use the language of calculus 3, that means the right hand gesture holds. Gesture compatible with the right hand gesture. Another way of saying that is that it is a rotation of the ijk system of vectors. So in this case, that means if we call this, let me use a blue color here. So if this is like your I, of course quotation mark, this is your J, and then this is your K, then you see that the right hand gesture holds. And as you can see, if here in this very picture, either we negate the ends, we look at the opposite of them, or we negate the orientation of C, we will be in trouble. The right hand gesture will not work. However, if we do both of them, we are still good. That means the other choice, and where the Stokes theorem will still hold, would be if C moves in that direction, and in that case we have the choice of normal vectors pointing downward. So if we have this two choices for the vector n and for orientation of C, again we are compatible. So in both of these cases Stokes theorem will hold, but if we only switch the direction of either n or C but not both, then the Stokes theorem will not hold. There will be a difference of minus sign. So that is a big restriction on the orientations that we fix on the surfaces. And the reason we are so concerned about them is that the notions of line integral and the surface integral depend on orientation. If you reverse the orientation, those integrals pick up a negative. So what does the Stokes theorem say? The Stokes theorem, so already my pictures have given away a lot of information. We have a surface S in 3D, it's orientable, and its boundary is a simple closed curve C, and we parameterize this C by some RT. And we fix a normal vector on S that is compatible with R prime of t in the above sense. Then the last ingredient is that we have a vector field in 3 dimension, which is defined on some open region in 3D dimension containing this whole geometry of S and the boundary and everything. Then the line integral of f along C will be exactly equal to the integral on the surface of curl of f. And again, the analogy to Green's theorem cannot be missed here. Integrating on the boundary is the same as integrating the derivative inside the domain. And again, as I said, if we reverse the orientation of C, this integral on the left will be multiplied by a minus sign. That's why these orientation things are sensitive. And that means to retain the equality, we must also multiply the normal of surface with the minus sign, and that will negate, put a minus sign here in this definition of surface integral. One of the nice applications of Stokes theorem, in my opinion, is that it shows the independence of certain integral from the surface. So suppose we have one fixed curve C, and we have two different surfaces whose boundaries are both this curve C. So red is one surface with boundary equal to C, and maybe blue here is a totally different surface which shares the same boundary of C with the other surface. Now, according to Stokes' theorem, in either case, curl of f integral along the surface S1 will be integral along the curve of f dr. But for the same reason, this will be integral over S2 of curl of f ds. So removing this intermediate one, it shows that these integrals are equal. That means integrating curl of a function does not depend on what surface you are looking at, and therefore if you have a complicated surface and you are trying to integrate along that surface a curl, you can freely ignore your surface and look at a much simpler surface, for example a disk whose boundary is the same. And this theorem says as long as the boundary is the same, the integrals will be equal. Modulo this orientation stuff that we always should take care of. Another interesting application to me is suppose we have a surface which doesn't have a boundary, so it's kind of a closed surface like a ellipsoid. So as a 2D surface, this does not have a boundary. It contains a volume and there is no edges, so this piece of paper has boundary and it's this thing, but this surface does not have any boundary. So S has no boundary, it's a surface with no boundary. Then double integral over S of curl of a vector field will always be 0. Now I want to show you how this follows from Stoke's theorem. So in this picture we don't even know how to apply Stoke's theorem because we don't even have a boundary. So what we do instead is we create a boundary. So we cut out a disk out of this surface and we completely remove it and toss it away. And now look at the remainder of this picture. It will be a surface with boundary, and the boundary will be exactly the disk that we removed. So this will be the boundary curve. And once we fix the orientation the right way, the integral, because here we have already fixed the normal, that means we pick the right orientation for the curve C. But once we do that, curl of f ds over the surface minus the disk will be equal to integral along C of f dr. Now let's take a limit. Let's take tinier and tinier disks. So we go back here, and instead of removing too much, we just remove a very small disk. And we again orient it, and we do that. And if we take the limit, what happens? If we take smaller and smaller disks, this integral goes to 0 because, well, f is a bounded function, bounded vector after all, and this C begins to have very small length, and that drives the integral to 0. On the other hand, if this goes to almost nothing, then this side converges to integrating curl of f on all of S, because what we have removed is negligible. And this equality was always true, and it holds also in the limit, and from that we conclude what we claimed, that curl of f over closed surfaces will always be 0. The reason also I mentioned this is that later we see the divergence theorem, we will see another justification of that. So another proof of this statement is through divergence theorem, which will be the last theorem and last topic of the course. So your WebAssign and your book has a lot of exercises on Stoke's theorem, and I refer you to them for some practice. But per se, both divergence and Stokes theorems are not that difficult, assuming that you're pretty comfortable with line integrals and with surface integrals of vectors especially.